Section 2.2, Linear Equations. Again, some terminology. A linear equation in one variable is an equation that can be written in the form ax plus b equals 0, where a and b are constants and a is not 0. Now, it doesn't mean that it will necessarily look exactly like that. However, what it means is that if we can manipulate the equation somehow and make it look like that, ax plus b equals 0, it's by definition linear. So I've got a couple here and it says, is it linear? And the first one says that 2 times the quantity x plus 3 plus 1 equals 0. Well, if I simplify the left-hand side, I would have 2x plus 6 plus 1 is 0, or 2x plus 7 is 0. And so this is linear, with a equal to 2 and b equal to 7. Similarly, 3x minus 5 is equal to x minus 8. It doesn't look linear right away, but if I subtract x from both sides, so that gives me 2x minus 5 is equal to negative 8, and then I add 8 to both sides, then I'd have 2x plus 3 is 0. Then it is linear, with a equal to 2 and b equal to 3. So now how can you easily determine if an equation is linear? Well, the key characteristic is look at the variable. If all you see is the variable, right? If you see just an x, and you don't see any power, right? You don't see it raised to any power, and you don't see any divisions by x, and you don't see any square roots, it's linear. So then, I've got some more equations here. Why is it not linear? The first equation is not linear because it's got an x squared. Not linear. We only want x to the first power. Remember, that would mean when we have x to the first power, it's usually not written at that first power. 5 over x plus 7 equals 0. This is not linear because we have the 5 over x. We don't want division by x. Or, in general, the variable. And what if we had 2 times the square root of x minus 3 equals 0? This is not linear because we got that square root of x. We don't want square roots. So that was just sort of identifying some linear equations. Now let's actually talk about how we can solve linear equations. One method for solving a linear equation is by using a table of values. And so let me demonstrate that by first completing a table of values for the given value of x. Then we'll solve the equation 5x minus 2 equals 3 using the table. So 5x minus 2, we want to let x equal negative 2. So we'd have 5 times negative 2 minus 2, that would be negative 10 minus 2 is negative 12. And then letting x equal negative 1. 5 times negative 1 minus 2 would be negative 5 minus 2 is negative 7. 5 times 0 minus 2 would be 0 minus 2, negative 2. 5 times 1 minus 2 would be 5 minus 2, which is 3. And finally, 5 times 2 minus 2 is 10 minus 2 is 7. So then the question, okay, so now it says now solve the equation 5x minus 2 equals 3. So we say to ourselves, where is 5x minus 2 equal to 3? 5x minus 2 is equal to 3 when x is equal to 1. So the solution of the equation would be x equals 1, or the solution set would contain 1. Now would be a good time to pause and try this one out on your own. Use a similar method as shown in the previous slide. Alright, letting x equal negative 2, we would have 9 minus the quantity negative 2 plus 3. And so that would be 9 minus 1, which would be 8. 9 minus negative 1 plus 3 would be 9 minus 2, which is 7. 9 minus 0 plus 3 would be 9 minus 3, which is 6. 9 minus 1 plus 3 would be 9 minus 4, which is 5. And finally, 9 minus 2 plus 3 would be 9 minus 5, which is 4. Finding the solution. When is 9 minus the quantity x plus 3, when is 9 minus the quantity x plus 3 equal to 4? That happens when x is equal to 2. So x equals 2, or the solution set would contain 2. So that's how we can use a table of values to solve linear equations. If we want to solve the equations using a symbolic method, here is a strategy that we can use. First, use the distributive property to clear any parentheses on each side of the equation and combine any like terms on each side. So basically simplify each side of the equation. Then use the addition property of equality to get all of the terms containing the variable on one side of the equation and all other terms on the other side of the equation, combining any like terms again. Finally, use the multiplication property of equality to isolate the variable by multiplying each side of the equation by the reciprocal of the number in front of the variable, which is the same as dividing by each side by that same number. And of course, it's always good practice to check your solution by substituting it in the given equation. So now let's see some examples. Solve the equation checking each solution. 8 is equal to 5 plus 3x. So running through the steps, I don't see any parentheses. I don't see anything I can combine. So I'll get straight to the addition property step. I only see one variable term. So I will leave the variable down that side of the equation, and I'll move the non-variable term to the other side by subtracting from both sides. This yields 3 is equal to 3x. Now I will use the multiplication property to divide both sides of the equation by 3. And this yields that 1 is equal to x. Let me check my work. Is 8 equal to 5 plus 3 times 1? Well, that's 5 plus 3, which is 8. Yes. Looking at the second equation, negative 7x negative 7x minus 4 equals 31. Now would be a good time to pause. Try this one on your own. Alright, I see only one variable term, this minus 7x, so I'm going to leave it alone. Let me add 4 to both sides of the equation. Then I would have negative 7x is equal to 35. Now I'll divide both sides by negative 7 to isolate the variable. And this yields that x is equal to negative 5. Checking my work is negative 7 times 5. I'm sorry, negative 5. Minus 4, is this equal to 31? Negative 7 by negative 5 is 35. 35 minus 4 is 31. So those were fairly simple. Let's make them a little bit tougher. Negative 2 by the quantity 2x plus 7 is equal to 1. All right. Applying the distributive property, negative 2 times 2x is negative 4x. Negative 2 times 7 is minus 14, and that's equal to 1. And now this is similar to the previous exercises. I will add 14 to both sides. And now I have negative 4x is equal to 15, and dividing through by negative 4. X is equal to negative 15/4. Checking the solution, we would have negative 2 by 2 times negative 15/4 plus 7, and we want that to equal 1. 2 times negative 15/4 is negative 15/2. Plus 7, I'm going to immediately write that 7 as a 14/2. 7 is 7 over 1. 7 over 1 is the same as 14/2. So that's negative 2, and then negative 15/2 plus 14/2 is negative 1/2, and those are reciprocals. It does equal 1, so that checks. I'll do this one as well. 6 plus 2 times the quantity x minus 7 is equal to 10 minus 3 times the quantity x minus 3. Now be careful here. 6 plus 2 is not 8, because this 2 is being multiplied by x minus 7. We must take care of multiplications before additions, like in the order of operations. So applying the distributive property, I would have 6 plus 2x minus 14 is equal to 10 minus 3x plus 9. Combining like terms on the left, I would have 2x, and I have a 6 minus 14 minus 8. I have a negative 3x, and 10 plus 9 is a plus 19. Now, here I have variable terms on both sides of the equation. So what I'll do is, I will move the variable terms to the left by adding 3x to both sides. That would give me a 5x on the left. While I'm at it, I'm going to add, so now that I have all of the variable terms to the left, I'm going to go ahead and add 8 to both sides to bring all non-variable terms to the right. So I now have 5x equals 27, and now I can divide by 5, and x is 27/5. I'm not going to check my solution on this one. I will leave it for you as exercise. Now would be a good time to pause, practice these on your own. Alright, applying the distributive property, I would have negative 2t plus 14 minus t minus 5 equals 5. Combining like terms on the left, I have a minus 2t and a minus t, so that's a minus 3t. I have a plus 14 and a minus 5, so that's a plus 9 equals 5. I only have variable terms on the one side of the equation, so I don't need to adjust the variable terms at all. And I will instead simply get the non-variable terms to the other side. So I now have negative 3t is negative 4, and dividing both sides by negative 3, I have t equals positive 4/3. A negative divided by a negative is positive. And again, I will leave the check for you as an exercise. The second equation on this line, let's first apply the distributive property. So I would have negative z minus 4, and here I just have this plus a quantity, so I can just write the terms. plus 3z plus 1. Right-hand side distributing minus 2z minus 2. Collecting like terms, minus z plus 3z is 2z, minus 4 plus 1 is minus 3, equals negative 2z minus 2. I have variable terms on both sides of the equation. I'm going to bring the variables to the left. So I will remove this minus 2z from the right by adding 2z to both sides. So I now have 4z on the left and no more variable terms on the right. Let me add 3z to both sides. Negative 2 plus 3 is 1. And dividing through on both sides by 4, z is 1/4. So now let's look at some equations that involve decimal numbers. Now we can work exactly like we did before, but if we have multiple decimal numbers, it might be useful to work with integers instead. And we can do that by multiplying through by a power of 10. And what we do is we decide what to multiply by looking at the decimal numbers. We say, what is the decimal number with the most decimal places? Well, this decimal number has 1 decimal place. So what I will do is multiply by 10. For each decimal place, put a 0 in that power of 10. And don't forget to multiply the right-hand side by 10 as well. So now multiplying, that would give me 55x plus 30x is equal to 510. Or, combining like terms, 85x is equal to 510. Dividing by 85, x would equal, let's see, 510 divided by 85. I think that'll be exactly 6. 85 times 6 would be 30, and yes, 510. So x equals 6. Why don't you pause and try the second exercise on this slide on your own. Alright, so looking at the decimal numbers, I see all of the numbers here have decimals, but I would look at and say, well, there are some of them that have 2 decimal places. So I would decide to multiply through both sides by 100. Applying the distributive property, 100 times 0.04 would be 4, so I have 4x plus 3 is 2x minus, now be careful here, 100 would move the decimal 2 places to the right, so minus 10. I see variable terms on both sides of the equation. I will subtract 2x from both sides. And I have non-variable terms on both sides, so I'll move the non-variable terms to the right. And dividing through by 2, x is negative 13/2. When we have fractional numbers in the equations, we can do something similar. We just have to choose the correct number to multiply both sides by. And the number that we would use is the least common denominator of all of the fractions present in the equation. So if I look at these fractions, 8, 4, 2, and 8, the LCD would have been 8. So I will multiply both sides of the equation by 8. So now I have 8 over 1 times negative 3/8 x plus 8 over 1 times 1/4 is equal to 8 over 1 times 1/2 x plus 8 over 1 times 1/2. Simplifying, now if you just think about how multiplication works, these 8's will reduce out, leaving a negative 3x on the first term. The 8 and 4 will reduce, leaving a factor of 2, right? Because this 8 is a 4 times 2, and removing the common factor, that'll leave a plus 2. Similarly, this 8 is again a 2 times 4, and removing the 2 leaves a 4x, and that shouldn't have been a 1/2, but rather a 1/8. And 8 times 1/8 is 1. So we now have negative 3x plus 2 is equal to 4x plus 1. And now we can proceed as in the previous examples. Subtracting 4x, subtracting 2 yields negative 7x equals negative 1, dividing through by negative 7. X would be positive 1/7. Try this second exercise on your own. Alright, if you used a similar technique, you would have found that the LCD is 12, and so you would multiply both sides of the equation by 12. And so we'd have 12 over 1 times 1/3 x plus 12 over 1 times 1/4 is equal to 12 over 1 times 1/6 minus 12 times x. Reducing carefully would give us 4x plus 3 is equal to 2 minus 12x. Variable terms on both sides, so I'll bring them to the left. Non-variable terms to the right. And that gives me 16x equals negative 1. Dividing through by 16. X is negative 1/16. All right. Let's look at these equations. And these don't look like those fractional equations that we had or the decimal ones. They look relatively simple, but there's something we have to be very careful about. All right, if we apply the distributive property carefully, we would have 4x plus 8 minus 4x minus 6 is equal to 10. If we combine like terms, 4x minus 4x, well, that would be 0x. We would not write anything in its space. But I'll go ahead and write 0x for a moment. Plus 8 minus 6, that would be a plus 2, equals 10. And 0x is 0. So we have 0 plus 2 equals 10. And so we have 2 equals 10. And we look at this and say to ourselves, huh? You know, can this ever be true? Is 2 ever equal to 10? In mathematics, this type of equation, which is false, right? 2 can never equal 10. So this statement is called a contradiction. And what this tells us is the equation has no solutions. If we look at the equation on the right, applying the distributive property, we would have 5x plus 5 minus 4 is equal to 15 minus 2x minus 14 plus 7x. Combining like terms on the left, we would have 5x plus 1. Combining like terms on the right, let's see, we would have a minus 2x and a plus 7x. That would be a 5x. And we'd have a 15 and a minus 14. That would be a plus 1. 5x plus 1 equals 5x plus 1. These are exactly the same. When this happens, this is called an identity. When this happens, what we know is the solution set consists of all real numbers. I could substitute any number in the original equation and it would come back as a true statement. And so therefore any real number is a solution. And so we often write it as the set containing all real numbers. An application. An athlete is 16 miles from home, running toward home at 6 miles per hour. Write a formula that calculates the distance that the athlete is from after X hours. All right, so when we have a situation like this, what we can say is that the distance, well, the original distance was 16 miles. He's running toward home. So the distance between his position and home is decreasing at 6 miles per hour per hour. That's 6 miles per hour. So we have 16 minus 6 times the number of hours. So there's part A. Part B. Determine D when x equals 1.5 hours. D would equal 16 minus 6 times 1.5. 6 times 1.5 is 9, and 16 minus 9 is 7. So determine D when x is 1.5 hours. D would be 7 miles. C. Find x when D equals 5.5 miles. 5.5 would equal 16 minus 6x. Subtracting 16 from both sides, we would have negative 6x is equal to negative 10.5. Dividing through by negative 6. Let's do a little bit of long division up here. 6 divided into 10.5. 6 goes into 10 once. Six divides into 45. Let's see, that would be 7 times. And bringing in a 0. 6 divides into 35 times exactly. So 1.75 is x. Interpret the result. So x is a number of hours. After 1.75 hours, the athlete is 5.5 miles from home. All right, and one more application. The cumulative number of HIV infections, N, in thousands for the United States in year X can be approximated by the formula N equals 42X minus 83,197, where X is greater than or equal to 2,000. Approximate the year when this number reached 970,000. Approximate the year. We need a value of X. When this number reached 970,000. Now the number N is in thousands, so we need to use this 970. So we will substitute 970 for N. And we now need to solve this equation. Adding 83,197 to both sides. We would have 42X is 84,167. So now we would need to divide by 42. All right, now we got to go through some long division here. All right, so let's see. 42 divides into 84,167. 42 divides into 84 twice exactly. 42 doesn't divide into 1. It doesn't divide into 16. It will divide into 167. So 4 times would be a little bit too much. So 3 times. And that would give us 126, and subtracting would give us 41, and bringing in a 0. It can't be 10 because that would be 420. It would have to be 9. So 2003.9, hey, that's about 2004. So the year would be approximately 2004.